Okay, students, let's begin lecture for today. We're going to be talking about uh, free fall by the end of class, and we'll have some homework. But before we do that, I'd like to just cover a few things that are new inside web courses. And specifically, as I mentioned last week, every day that you have your iClicker registered through web courses, you'll get a bonus point for that lecture. And I have done that for the students that were registered by Friday, by Thursday lecture. And in fact, I didn't update the roster until about 10 o'clock on Friday, so there's a little bit of extra time. For people that were registered, they get one bonus point. Now, if you're new to UCF, if you're a newbie to Canvas, you'll see a little icon over here, a little alert icon by grades. And this indicates there's one new grade data in there for this particular student. And when you click on the grades page, it'll look like this. So this is the test. This is my, kind of hokey test student account that they give every instructor. Anyways, this is what the grades are. So you can see homework here. Homework's up at the top. And we got some early iClicker stuff. And you can rearrange it by due date and whatnot. But anyways, what I want to point out to you is this one, the early iClicker registration for January 12th. That was last Thursday. Okay? And so if you've looked in your grades and seen, oh, I got a bonus point. Yeah, that's because you were registered through iClicker, you were registered through web courses before about Friday morning, 10 o'clock. All right. Now, if you registered over the weekend, and I know many of you did, you'll get a bonus point today. All right. And that's this one down below here, January 17th. Hey, did you know that the numbers for today? 1717. Sweet. And I wrote in, and the bus I rode in on today was number 17. And it traveled on Highway 417. Man. So that means, a lot. Anyway, here's your point over here. 1. And it doesn't seem like 1, but it doesn't seem like a lot. But if you got that one, you're going to get 4 more automatically because you're registered for all the next 4 classes. If you register today, if you have registered for today, you'll get this one down here. All right. Now, before I continue, I want to mention something that students in the previous hour came up and talked to us about. And that is that if you're on a Mac or an iPhone or iPad, the Safari browser is a little tricky for registering. And there's a couple ways around it. A, you can use Google Chrome. B, you could go to the library and use one of the desktop dinosaur computers over there in the library. C, and I just learned it last hour, in Safari, if you enable cookies for Canvas, which I can't remember how to do it. I'll have to look it up. But apparently the student had trouble registering. He said, yeah, I enabled cookies. I registered, worked good, and then I went back and disabled cookies. All right, so that is option C if you're on a Mac. If you're on a Windows computer, I don't know, or an Android, I don't know but I know a lot of you guys have registered, which is great. Now, another thing I want to point out to you about the numbers up here, and this applies in general to any bonus point activity, including these. The out of number is 0 for bonus points. All right. Now, what that means is you don't use bonus points at the end of the semester anyways when you got them all the ones that you're going to get. You use them to if you're trying to figure out a percentage for the semester, you put the bonus points in the numerator, but you don't put them in the denominator. Now, if you look up here at homework 1 that you had this weekend, a 5-pointer, and hey, you guys, if you accidentally didn't do number 1, it's not going to kill you because we're going to have like last semester we had 270 something homework points. So missing 5 out of 270 is not going to be great shakes. But hopefully you get all your homework done. And if you do get a low grade on a homework, it's going to be something out of 5. So, for instance, if you get 4 questions right, or 4 points for homework 1, that'll be 4 out of 5. That's 80% on that assignment. And then the total homework grade is based on all the out of numbers added together and put in the denominator. A bonus point does not affect the denominator of any percentages. Okay? It only affects the numerator. That's basically what a bonus point does. Okay? It can only help you. Missing it cannot hurt you. Getting it can help you. Right? So it's never negatory. It's never harmful. And that's because it's out of 0. It doesn't really add to the baseline. Our baseline for pointage for the semester is 250 points. 100 points for the final, 100 points for 2 midterms, 25 for homework, 25 for class participation, zip zap. That's it. All right? So the denominator at the end of the semester, no matter how many bonus points I set up, is always going to be 250 in the denominator. And the numerator is however many points you get. All right? So the bonus points always go in the numerator, never in the denominator. Question?
Are all the homeworks out of 5 points?
No. The question was, are all the homeworks out of 5 points? And the answer to that is no. There's going to be some ginormous ones. So, and the reason that this one was fairly small is because usually the first week, there's a lot of adding and dropping and, so I try to make homeworks, like homework 0 was just 1 question and for attendance. And then homework 1 was fairly small, just a little bit. But believe me, there'll be more homework. I know everybody likes homework, so we'll make sure to have plenty of it. Anyways, questions about the bonus point situation? Question over here somewhere? Okay. All right, let's keep going. I want to discuss a couple things. I've been taking a traffic safety course for various reasons, and I noticed I was reading it this morning actually. I noticed that and they had this blurb: your stopping distance is greater if you're speeding. And not that I know that nobody in here speeds. You're all very nice, good citizens and everything. You abide by the laws and so forth. But for the people that are bad, they have to reinforce that your stopping distance is greater when you speed. If you double your speed, your distance required for braking will be 4 times longer. And that is accurate. 2 to the second power. And so the reason I bring that up is by the end of not by the end of the semester, but by the first test, you're going to understand why that's the case. Why it's 4 times longer. Not double, but 4 times longer. There's another blurb in there, and this is a screen grab. It says, the statistics we've reviewed clearly tell us that speeding should be avoided, as it is illegal and makes driving much more dangerous. And then the fourth bullet down says, your force of impact in a collision is much greater if you're speeding. And then the last sentence in that same bullet, by increasing your driving speed by only 10 miles per hour to 35 miles per hour, the force of impact doubles. Now, force of impact and the doubling factor, you're going to understand that in the next couple, 3 weeks as well. So the stuff that we're going to be studying, the stuff we're putting together, is going to allow you to understand, for instance, stuff in that driver safety course. Now, hopefully you won't have to take one of those. But if you do, you'll know why they wrote the things that they write in there. Now, I want to recap last lecture, and I generally do a little bit of a recap, sometimes a little bit more at the beginning of lecture. We talked about Galileo and his idea, his conviction that that nature itself wasn't random. I mean, it was intelligible, that nature is intelligible, and that he compared it to a grand book, an enormous book written in a mathematical language. And so his concept was that a conversation, if you will, could be established that used a mathematical language as well as the regular vernacular languages, Italian and English and stuff. Galileo wrote a lot in Italian. In his day, people wrote in Latin. They still wrote in Latin. But he also wrote a lot in Italian. Anyways, his whole philosophy was that we can have this conversation, we can teach ourselves, we can learn through observation and measurement, and exchange information as if we're in a school. And you guys are in this school now. Galileo's school, the school of science. And that it was based on his conviction that there is something inherently mathematical in the comprehensible language that the physical universe presents to us every day. If you have eyes to see, and if you have the skill to measure, various things like distances and times and so forth. Here's his number one student. So we're following in a grand tradition. And for us, it's about 400 years old, the scientific tradition. And so our great-great-grandsters, Galileo and Newton and all the rest, we're following in their footsteps. And we're going to be replicating some of their concepts and some of their thoughts today. We're going to actually not replicate, but try to tackle and make sense of some of their concepts today. Another thing that we did last time, we talked about velocity and how making position and time measurements allow you to figure out how fast and where something is going. It's also discussed in chapter 1. Now, we talked about how to calculate a distance, using a right triangle maybe, or maybe just doing a subtraction, a delta x, if you're just going along the x-axis, one-dimensional motion. Coordinates, the x-coordinates from position A and position B. Now, that's over here in this expression, delta x equals x subscript B minus x subscript A. And you guys, as I mentioned last time, and as I'll mention again today, the order is always, for a delta something, delta anything, it's later minus earlier. So the later position is position B. So the x-coordinate of position B minus x-coordinate of the earlier position, position A. Same thing for the elapsed time, which you also need for speed. And that's based on different measurements, temporal measurements, clock readings basically. And your stopwatch on your cell phone, or if you actually have a stopwatch, that is actually computing delta t from time t equals 0 when you start it to time t equals whatever when you stop it, and it gives you the elapsed time. But it's basically making very, very fast clock readings. We use those calculations, delta x and delta t, to figure out the speed And here's this big formula up here. The speed is, or the velocity is the ratio of change in position divided by elapsed time, delta t. We also had it in homework 1 and number 3. I want to double check number 3 with you. Here's the image for it. This individual walking down and bumping into this doorway. And right here are the data that you need. Let me turn off my sound here. Hold on. Right down here are the data. Now, we're going to review this, and I'll sometimes review homework in class. Maybe 1 or 2. This one, most of you guys did good. I looked at it early this morning, and your performance was pretty good. But just for safety, let's review it. Here's the data, event 1 and event 2. You can jot it down again if you like. Compute delta x first, x2 minus x1. All right. And on this one, I made x1 a negative number so that I could remind you that it's a subtraction, and that in this case, subtraction of a negative is the same as an addition of a positive. All right, so 0 minus a negative 2.45 is the same as 0 plus positive 2.45. Right, and so there's your answer for delta x. Something similar for delta t, t2 minus t1 in the homework. Delta t of 0.74. Now, you can do that on your calculator, or you can do it on pencil and paper, and then here's your actual calculation. The speed is delta x over delta t. And that's 2.45 meters divided by 0.74 seconds, and that works out to 3.31. Now, let me, meters per second. Let me point out that on the homework, you were to type in the numerical part of your answer to the nearest 0.01 meters per second. But you weren't to type in meters per second, just the number, the numeric part. And I think most of you did that. And on homework and in lecture, on exams, I will always tell you how to round off your answer. In other words, I'll always say, give me your answer to the nearest 0.001 meters per second, or to the nearest centimeter, 0.01 meter, or to the nearest kilogram, or to the nearest 0.1 of a kilogram. Whatever it is we're trying to measure, I'll always specify that for you. You'll always be typing in a number. You won't be typing in meters per second or kg for kilograms or anything like that. Now, if we were doing written tests, yes, you would type that in the normal manner. But for us, using clickers and using Canvas for homework calculations, no, you cannot do that. So you just be typing in numbers. All right. By the way, you can make a note. The homework number 3 is similar to the example on page 10 of the e-text. And hopefully most of you have gotten the e-text going by now. Now, let me pause for questions on this homework assignment. Okay, let's keep going. I want to follow up with you concerning the idea of average velocity and instantaneous velocity. Now, those are 2 vocabulary terms. You should consider them things to know. And we are going to learn and know about them by talking and by calculating and kind of thinking things over. And one of the examples that we're going to talk about today is the tortoise and the hare, that famous fable from Aesop's Fables, tortoise and the hare. So let's get down to the idea of average and instantaneous. Average is based on several measurements, a finite number. In the case of a velocity, it's position and time measurements. So for instance, in the homework, in this question, number 3, it was basically 2 snapshots worth of data. A snapshot of position and time for event 1, and then another snapshot worth of data at time t2, when he runs into the door. Okay, but it could be something else. You could have, if you have 3 different sets of measurements, all right, you just add them up and divide by 3. I mean, it's always, for an average, it's add them up and then divide by how many. All right? So if you have 7 measurements, you add them up and then divide by 7. Ding, that's your average. All right, and that's what, and the thing about an average velocity is, like the one that we calculated just now for homework 1, number 3, is it doesn't necessarily tell you what his velocity state is at any intermediate time. It tells you his position at time t equals 0. It tells you his position at time t equals 0.74 seconds, but that's all it tells you. And the average velocity, he might be going faster, the same speed all the way, or maybe faster, and then he took a break, and then he started again. Although it's not really plausible for a human to take a break during a time interval 3/4 of a second in duration. But anyways, theoretically, it's possible. And the definitely plausible and believable and understandable example is the tortoise and the hare fable. Now, you'll notice here that I've made in parentheses a reference to chapter 1, section 11. And I will try to be doing that in my keynote slides that you see in lecture. And Miss Caroline right now is typing little note blurbs into the Twitter feed. If you haven't already subscribed to the Twitter feed, I invite you to do so. And you'll be able to look at all the notes, Caroline's notes as she takes them. And actually, that's a pretty good idea. Darian does it sometimes too. Because these guys know how I think. So when they take notes, those are good notes, all right? And it's a resource that all of you can take. And when it's appropriate, they will insert a reference to a homework or to a page in the textbook. In this case, a section in the textbook. Another example that brings out this idea of instantaneous and average is the Turkey Lake Service Plaza example, and that's on page 11, chapter 1, section 10. So you can go and look at that. We're going to look at and talk some more about the tortoise and the hare, though. So that's our main example to discuss this idea of instantaneous and average. All right. So there's 2 basic assumptions in this fable. And Aesop, when he wrote, I don't know if he wrote it down or shared it verbally or whatnot, but anyways, in the fable, they weren't really thinking of physics. But one thing is true, and that is that the tortoise, once the tortoise gets going, his speed is, at any instant of time, is the same as what will eventually be called his average. And the way that I describe that in the textbook is with this graph. Now, this is a velocity versus time graph. We're going to be talking about these at the wazoo today. And this is the first one. And it basically just shows a chart or a graph of the speed of motion of the tortoise every second. All right, so it's basically like a speedometer rate. And a speedometer reading every second. And the tortoise, as the fable goes, he gets going. So he starts from 0, and for the first second, he's at half speed. And then for the second, he's up at full speed. And full speed ahead for him is not very fast, but he stays at it. And it's just nice and smooth all the way to the end. And of course, the fable is that he wins the race. And that's because the hare's velocity state changes several times during his race. Now, the corresponding velocity graph for the hare in the textbook is here, right? This velocity graph. So they're kind of overlapping so you can see them. And this one I made to be just kind of a jumble of different velocities. And he gets greased. He loses the donuts from Dunkin' Donuts. So, tough noogies for the hare. And it's the moral of the story is keep going. Even if you're not moving fast, if you keep going. It's kind of like UCF. You can't finish. You ever feel that way? Just keep going. Just like the tortoise. You'll win the prize. Anyways, another way to think about it is to say that the instantaneous speed represented by the phrase v of t, or the speed at time t being a generic symbol for any time in the indicated period. So in the first 30, actually I think these are minutes, 30 minutes of time. Anyway, v of t is constant for the tortoise. All right, it just completely, it's slow. It's not very big, but it's the same, nice and steady all the way across. And v of t for the hare, all over the place. All right, so this is 3 different ways to describe the instantaneous velocity state of the hare and of the tortoise. Okay, number 5, that's one way to look at it. Number 6, that's another way to express it. Galileo said that, or was convinced that we'd be able to write true sentences using mathematical structure, and 6 is definitely that way. Here's a couple of true graphs. That's the third way, the 2 velocity graphs. One from the hare, for the hare, and one for the tortoise. And by the way, you guys, those 2 graphs are copied right out of the textbook. So you'll see those when you finish reading chapter 1, which will be part of your homework tonight. Now, there's one more thing. This is a close-up on the hare's graph that I want to emphasize to you. So hopefully you can squeeze in one more bit of information or comment. And that is that the tortoise's graph is nearly rectangular. The only break from rectangularity is down here. Otherwise, once he's going, yeah, it's rectangular. When he's just starting up, he's got a little bit of variation here, but it's nearly rectangular. So, and that is actually going to be helpful for us, or highly useful, as I have written here. So what we're going to do now, and this is now getting into the heart of the lesson for today, we're going to start making some abstract graphs of velocity versus time. And the first one is going to be a abstract graph of constant velocity, just like the tortoise, versus time. All right? And the velocity graph is going to be just like those diagrams from the textbook. There's going to be a vertical scale, and I'm going to include the negative side to represent leftward motion. A positive velocity means rightward motion. And then the horizontal time is going to be the time axis. So vertical axis represents velocity. Positive is rightward. Negative numbers below the time axis indicate negative or leftward motion. The horizontal axis represents time. Now, normally we're going to anchor it to time t equals 0. Right, kind of like out there at Cape Kennedy, the Kennedy Space Flight Center. Time t equals 0 is ignition. T minus 30 seconds and holding, that means they're ready to go in 30 seconds, but they've got everything on hold for last minute double checks, last second double checks. Then they start the countdown and they hit the button to start the engines at time t equals 0. So we're going to do the same thing, but we don't have to, but that's what we're going to do. And for this example, let's graph about 2.5 seconds. And what are we going to graph? We're going to graph an object that is moving at a constant velocity of 1 meter per second rightward. So its graph is a horizontal dashed line up at +1. Now I just saw a student up here in the front taking a photograph of this. And it's not really, now you're not in trouble, and I see students doing it all the time. You don't have to do that because all the lectures are recorded and podcasted, and YouTubed as digital video. So all the notes, diagrams, and my narration are on those YouTubes. So you don't have to worry about, frantically copying everything down that I write, or even everything that's on the screen. Just write bare bones notes, and then go back and fill in the notes, the bare bones, flesh it out by re-listening to the lecture in YouTube. And the value of that is you can go back and forth in YouTube as many times as you like to re-listen and re-look at all the equations and diagrams and notes that are on there. You can listen to it to your heart's content. Darian and Caroline have both done that profitably when they were students. So if you want to get an A like they did, that's a good study tool to do. And it makes things a little bit better during lecture because you don't have to slavishly write down everything that I say. Just write down the high points and listen to what I say instead of trying to copy, what I say. All right? So this horizontal line, this is the graph, right? This graph represents the motion of this particular object. It's moving 1 meter per second to the right for a time interval between 0 and 2.5 seconds. All right? And notice, and a side note, this is similar to the tortoise graph on page 13 that we were just looking at. And my final comment to you is an important one, and I want you to note it down carefully. A velocity graph encodes all instants of time, and it does so visually as a picture. And I want to mention to you that I am a visual thinker. And whenever I'm presented some kind of a problem, my first instinct is always to make a sketch or a diagram, if I can. Some of you may be like that, and I'm bringing it up for this reason. It's unusual for a scientist to be a visual thinker like that, but that's what I am, and that's why I like to emphasize these visual graphs that encode so much information visually. It's kind of interesting. The human mind, I'm going to be asking you some questions here eventually. Your eyes, your visual perception is extremely powerful. And here's an example of why I say that. A little baby, within a couple days of being born, can visually recognize mother and father. From all the other faces it looks at, it knows mom and dad. And we can't, the FBI can't get computers to do that. We can't get computers to do that we can do it, but it's not easy, it's not infallible. But a little tiny baby, 2 days old, 3 days old, yeah, they can do it just like that. It's excellent. So your visual intelligence, your visual perception is extremely powerful. Every single one of you, in the sound of my voice, your visual perception is enormous. So we're going to make use of it. Now, let me ask you this question. No, let's keep going. I'm gonna ask you a question. I'm gonna try to burn your brains here in a second, but let me keep going. Okay, what I want you to do is now shade in the rectangle between the graph and the time axis. So, but kind of like this, right in here. Just make up a nice rectangle between 0 and 2.5 seconds horizontally. And then between the graph itself and the time axis. So it's just a regular old rectangle. No great shakes, but that's... And what I'm going to ask you, and what we're going to try to do, is to answer this question, number 8. All right, the graph straight line represents the velocity nicely for all instants of time. Good, nice, fine, perfect, good. But what does the enclosed rectangle represent? I mean, it's up there. Does that represent anything that's useful to us? And the answer is, well, let's take a look. All right? Now, how do you compute the area of a rectangle? You remember the formula? Yeah, base times width, base times height. Or base times height, length times width, different ways to put it. Okay, base times height. All right. Now, what is the base for this thing? It's not measured in meters, because this is an abstract graph. It's not a graph paper graph. It's not XY graph paper. The base is a temporal measurement, 2.5 seconds. The height is a velocity measurement, 1 meter per second. So go ahead and write that down. And the area, the abstract area of this figure, this rectangle that we've constructed based on the coordinate system of the velocity graph and the graph itself, the dashed line, it forms a nice little old rectangle. Okay? And so the area, it's not really like, square centimeters or anything. Matter of fact, how does that work out? Do you see anything in that calculation that we've got there that you can, we've got a speed, we've got a time. Anything you can do with that expression to simplify it up or change it up, or what do you see? Right. Look at this. Seconds over here in the base and per second over here in the height, ching, they cancel out. All right? So take out your red ink pen and just cancel those babies out. All right? And the result is a distance in meters. And therefore, we now have an interpretation for the rectangle, not the graph. The graph is a representation of velocities. The area of this rectangle, formed by the graph, the time axis, and the two coordinates, is an area. And it is interpreted physically as the distance. Specifically, the distance traveled from the initial point, wherever it is, to the final point. We know how far the final point is away from the initial point. Now, a couple things I want to point out to you. This graph and the rectangle are good, but they don't contain position information. They contain velocity information. So you don't know if you're in Dubuque, Iowa, or Altoona, Pennsylvania, or anywhere else. But you do know from interpreting this that you're 2.5 meters further away to the right, so over here at 2.5 meters, from wherever your feet were at time t equals 0. So if at time t equals 0, you were on the corner of 3rd and Main in Dubuque, Iowa, then 2.5 seconds later, you're 2.5 meters out in the street, in Main Street, and you better be alert because you don't want to get run over by the trucks out there on the road. All right. So so side note, this picture does not encode everything. Right? It encodes velocity and encloses changes of distance, or you could say changes of the x coordinate, if you want to get fancy. And you can figure out delta x from this. Matter of fact, this particular result is completely consistent with the distance formula that we talked about last Thursday. Distance equals speed times time, or delta x equals v delta t. Right? And that's a formula that came straight from the definition of velocity. V equals delta x over delta t. Right? So this is perfectly consistent with that. Now, I have a question for you. Now I'm going to ask you a brain-burning question. And hopefully this will challenge you in the deepest recesses of your mind. And the reason I love asking questions like this is because it is a visual question. I want you to think visually. Use your visual cortex. What feature of this graph, the dashed line, so I'm not asking about the rectangle, but just the top of the rectangle, the dashed line. What feature of this dashed line represents the fact that this object has constant uniform velocity? In other words, how do you know by looking at this graph that it's constant uniform velocity? What do you think? The slope is constant. You're warm, but not quite. In the back. Yeah, you. It's horizontal. Its slope is constant, and in fact, the slope is 0. It's not tilted up, it's not tilted down. All right, so make a note of that. The horizontal velocity graph shows or represents uniform constant velocity. All right? So if something's speeding up or slowing down, we might have some tilt. The speed's changing. Maybe it's slowing down or maybe it's getting faster, But if it's constant velocity, nice and smooth. Just like the tortoise's velocity graph, nice and smooth almost the entire way. All right, now I have an iClicker question for you. All right, so get your clicker out. And for those of you using it for the first time, hold the power button down. That was the problem with the guy over here.
Yeah, I think so.
Okay. If you're using it for the first time in my class, hold the power button down until the rectangle flashes and then hit the B button twice. That's our frequency code. Now, if you're using your iClicker for biology class or history or something, the instructor there might be using a different code, CA or something like that. In that case, you got to hit the power button and type in that code. And when you come back here, you got to type it in BB. All right? So just try to remember that. All right, so iClicker question. And this one, another visual question that's coupled up to some verbal written concepts. Okay, so you're going to be using your visual thinking and your verbal thinking. Okay, try to get them consistent to match up. Here we go. Each dot represents a snapshot of the position of an object moving from point A to point E, with elapsed time delta t equals 0.1 second between flashes. Which of the four options is true? Very interesting. Look at that. It's interesting. You know, we can see how you guys vote up here. It's constantly changing. Very interesting. Just think. Make a decision. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 89 students answered. Go ahead and switch to. And this is interesting because look at that. There's a definite distribution of answers. In other words, you know, like we had one question last week, everybody got it right. I think the second question. This one we've got, and you know what it tells me? We got a little bit of a little disagreement going on here. Right? Most people have voted for option B, and option B. Go ahead and switch it over. Option B is correct. Okay, the object is slowing down. Okay, but a bunch of you voted for option A, some for C, and some for D. Now, for those of you that voted outside of option, other than option B, let me ask you, for those of you that did vote for option B, let me ask you, what is it visually about this image, this simulated strobe image, that tells you it is slowing down? How would you express that in the back? Yeah, that's not bad. The amount of distance between each succeeding set of dots is smaller, right? All right, so make a note of that. If you didn't answer option B, make a note of that. That's not a bad way to say it. Here's another way to look at it. Over here, in 1/10 of a second, it goes quite a way. So it's really booking over here. But over here, it's just kind of poking along. All right. So from really blazing over here in the first second, or the first 1/10 of a second, to just kind of poking along over here, that means, yeah, it's slowing down. And it's based on the fact that the distances between successive dots are getting smaller. All right, now that's a sign that you're dealing with a slowing down object. And second side comment on this. See, I've given you these questions. You know, the other day we had a Chuck Norris question. That just was for screwing around, just so you can know how to use your clickers. All right, and we'll occasionally do that. But normally we'll have questions that are meant to get you to think. Now, what I want to make as a side comment on this one is the following. This is a representation of motion that you've interpreted visually, and it is something that you could take a photograph of. In other words, you could set up a gigantic piece of graph paper with a camera overhead, a strobe photo going, and you could, maybe have something that slows down, with friction in just this way. And with a set of 5 images, 5 snaps of the camera, you might actually see this on XY graph paper. This is not an abstract representation, not in the way that the velocity graphs are. But we're going to do another velocity graph that is abstract, and this is the important one. And believe me, when I say important, I cannot overemphasize it. This is the strobe photo image, simulated strobe photo image of something slowing down. Now we're going to make a velocity graph. Okay? To do that, we're going to have to trot out the definition of acceleration. It's simply the amount of velocity change delta v in a certain elapsed time. So if something's slowing down, its v is changing, so delta v is, positive or negative. Negative if it's slowing down. And delta t is, some amount of time. And if that's happening, then the acceleration a is, just the quotient of delta v divided by delta t. Now this is similar, but not the same as delta x over delta t. That's the speed or velocity formula. The definition of speed or velocity, delta x over delta t. This one is the definition of acceleration. Now, from this, we can get a cousin equation by cross multiplication that gives us a change in velocity if we know the acceleration. Here it is. Delta v, change in velocity. If I know a in the elapsed time, I can calculate this. Right now, we're going to need this cousin. This is like its cousin from the other side of town, right? And but it's basically it's based on that definition: a equals delta v over delta t. All it is just cross multiply delta t to the other side. That's it. All right. Now, definition of acceleration. So let's use that now, and let's do the velocity graph of an object that is slowing down. Here it is. This represents an object slowing down. It starts out over here at time t equals 0 on the vertical axis at 3 meters per second. So it's up at +3. But then it slows down to a stop at 4 seconds. All right? So draw in that graph. And it's going to give you, the graph is the red dashed line. And it's going to give you a triangle. Go ahead and shade in the triangle, however you like to shade it in. Right? And 4 seconds later, it comes to a stop. Okay, now this is another graph. And this is for an object that's slowing down. So visually, what you see here is not a horizontal velocity graph. That's for something that's got constant velocity. This doesn't. It's slowing down. So we've got a little bit of tilt. All right? Something that's speeding up would be tilted the other way. It'd be going up to the right, like this. This one's going down and to the right, slowing down. That's all right. We can use it, right? So this is like, you take a penny and you slide it across a long table, and eventually it'll come to a stop. Right? That's what this is. Right? Now, what's the formula for the area? Because that's what we're going to try to tackle. We want to interpret the area of this one now. The area between the graph, the red line, the red dashed line, the time axis, and the initial time on the v-axis. Now, what's the area of a triangle? Remember the formula? Length times width times height? No. Base There it is, 1/2 base times height. Remember it? 1/2, let's do it. All right, so area, good old 1/2 base times height. Easy as a walk in the park. I mean, hopefully everybody remembers that. And you know what? All the rocket scientists down there at NASA, they work with this thing all the time. All right, I can tell you. So in terms of our example, the base is 4 seconds, and the total change is 3 meters per second. So you start at 3, and you finish at 0, so your total change is 3 meters per second. Right? So that's the change in the, the change in the position of the graph. It goes from 3 meters up over here and 0 meters per second over here. Stopped. Right? And guess what? We can do the cancellation again. But before you do that, I want to show you a little bit of fancy footwork. Right? Now, we're going to go slow so that you don't get caught napping. Because if there's one thing you do not want to do in this class, it is you do not want to get caught napping. Right? Now, I'm going to rearrange the 1/2. And I'm going to park it underneath that delta V, 3 meters per second. That's my delta V. That's my change in speed. All right, from 3 down to 0. All right, and just to remind you, here. I told you we were going to use that formula, delta V equals A delta T. Yeah, here it is, right here. Okay, we could even figure it out what the value of A is. But for now, let's just use this. All right. So the numerator there is 3 meters per second. And the denominator is 2. And we just kind of rearrange things. Nothing, no great shakes. Just kind of basic algebra. And now, I told you that 3 meters per second is your delta V number. But there's another way of looking at 3 meters per second divided by 2. 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 3 meters per second. What's the initial speed? The initial speed is 3. What's the final speed? 0. What's the sum of initial and final? 3. How many speeds did we just add up? So 3 meters per second divided by 2 is the same as what we just did. It's an average speed. That's right. This is an average speed. So here we go. This thing that we've got here, okay, we're going to keep in mind that we've got delta V up here, but this whole quotient here is an average speed. And then I got my delta T. Now, distance is a speed times a time. We're looking good. We already did that. Average speed times delta T, distance. Ching, got it. This is looking great. But we also have the fact that the average speed is A delta T. There's your delta V up there. So go ahead and instead of putting delta V now, put A delta T. And then put that 2 underneath. We're not doing away with that. It's not going to disappear. We still want that. All right? And so your average speed, so let me just push it up here. Okay, average speed. A delta T over 2. All right? And now let's put it all together. We're going to keep delta T here. And then instead of average speed, we're going to put in this quotient here. All right? So here we go. There it is. Delta T times the quantity a delta t over 2. Now, so far, it's looking, kind of shaky. I mean, we got a big jumble of symbols and stuff. But do you notice anything about this big mishmash of symbols? What do you see? What do you see? Delta t's in there twice. So that means we can replace it with delta t quantity squared. Why not? Now, there's nothing to do with the a, and there's nothing to do with that 2 in the denominator. So we're going to leave those the way they are. So the formula for the distance traveled, it is a distance, under a slowed down acceleration, 1/2 at squared. All right, and that is based on the combo of what we already knew about average velocity and what we knew about the definition of acceleration. Those two concepts put together get me this formula. In general, if you're speeding up from 0 or if you're stopping, this formula will tell you the distance. From the minute you start to slow down or from the instant you start to speed up from 0. Okay? D equals 1/2 at squared. And this is the formula that I like to call the distance triangle formula. My wonderful students, this is a general result. And it is a result that all these guys over in the engineering department would have to use calculus to derive. But we didn't use any calculus, did we? You know what we used? We used our brains and our visual recognition skills. So I always like to call this visual calculus. So when you go home tonight, you can tell your parents or tell your worst enemy if you want to confound your enemies. Yeah, we did visual calculus. We did calculus in physical science today. No big problem. It's easy. And the engineering majors will think, what the? Calculus easy? And they'll be jealous. They'll be jealous of everybody here. But yeah, that's what we did. Visual calculus. And this is a very, very general formula. Second comment, in addition to this being visual calculus that I bet no engineering major would be able to come up with this concept or knows this concept. Very few. Any engineering majors in this section? There was one in the morning section. He said, yeah, you're right. Probably hardly any of them. Second comment. Half the PhDs on the planet work down there at Mission Control in Houston, mapping out the trajectories of spacecraft between here and the moon, and that movie that just came out, Hidden Figures, which I got to go see it this weekend. Those mathematicians, you know what they were doing? Distance triangles and distance rectangles. And they were doing zillions of them. Because for a rocket, you have to do it every millisecond. And think of how many milliseconds there are in a second. And how many milliseconds there are in a minute. And how long does it take to orbit the Earth? 90 minutes. For the movie John Glenn, it's about an hour and a half. Still, the space station, the shuttle, about 90 minutes. Usually they're about the same orbit. So that's what they had to do. And believe me, when I program quantum field theory for black holes in the early universe, half the battle is training the computer to do a bunch of distance triangles and a bunch of distance rectangles in the exact at the same time and simultaneously and according to the forces that I encode in there. But that's all they're doing. And so now you guys know, as the saying goes, the rest of the story. When you go see that movie, Hidden Figures, Yep. You know what they're doing. You won't have to. I haven't seen it yet. Hopefully they haven't. Hollywood, they always take liberties, But hopefully they didn't take too many liberties, because this is not science fiction. This is real science. This is what they do. And now we got computers to do it. But back in those days, in the Hidden Figures days, computers were expensive, big, and slow. And so they had to have a lot of humans backing up the computers to make sure that they didn't blow it. Because they don't want somebody to, they don't want somebody to land in Kansas. They want them to land in the Atlantic Ocean, as fairly close to Cape Kennedy as they can make it. Anyway, so distance triangles, or in general, distance polygons. Third comment. We did the velocity graph for uniform velocity. We did the velocity graph for uniform slowdown. Nice, smooth slowdown. But sometimes, if you're in a car, you don't slow down at the same rate, so you won't have a nice flat or a nice straight line. It might have a little curvaceousness to it. All right? That's normal. The way you handle any kind of a curved velocity graph, a bunch of little tiny velocity triangles and a bunch of little tiny velocity rectangles. That's it. That's how you handle it. And you know what that is? That's calculus too. Just making your triangles and your rectangles as small as you can, and then just doing it a million times. So, all right, let's dismiss. Whoa, 10 minutes early. Good. We covered everything we need to. Your homework assignment, no regular homework, but study to the end of chapter 1. You're dismissed. Lights on, please. Yeah. Hold on a second. Let me turn off the recording.